Hi, in this lesson we are going to discuss the use of object proposals as a means of extending our CNN classifier into an object detector. Object proposals were originally used to guide the search for objects, thereby avoiding the computational burden of exhaustively sliding a search window across an image pyramid. Detection proposal methods are based on low-level image features, and they use these features to generate interesting candidate windows for classification. These are very similar to the feature detection techniques we spoke about earlier in the course.
The sliding window paradigm of exhaustively searching an image for potential objects at every possible position and every possible scale is computationally expensive and inefficient. Instead of this, we're now going to look at techniques called object proposals, which generate potential bounding box locations for further analysis. Goals for our object proposals include high recall under all conditions. Recall is a measure of how good an algorithm is at not missing any true positives. Precision is a measure of how good the algorithm is not getting it wrong, that is, not having false positives. Any algorithm we choose can be imprecise, as it will be feeding an accurate classifier. However, it must not miss any potential objects, therefore it must have very high recall. It must be capable of handling a variety of conditions, including different lighting, colors, and textures. Objects can also occur at any scale within the image, and so it must be capable of handling different sizes of objects and different aspect ratios. Ideally, we'd like to find objects of all shapes, that is, that the proposals be accurately generated in a manner that is agnostic to the type of object being detected. Finally, it needs to be efficient. It must be fast to compute. Objectness was one of the first object proposal generators. It ranks a number of windows per image according to their objectness score, which is a measure for how likely the window is to contain an object. The score is calculated from measuring characteristics of objects, such as differentiation from surroundings and having a closed boundary. These are determined using image cues, such as saliency, how distinct an object looks, color contrast, edge density, superpixel straddling. Most of the surface of an object in a window is covered by superpixels contained entirely within it, and by window location and size. Of these cues, superpixel straddling was shown to outperform all the others. Accuracy of the objectness measure was seen to be a function of the number of windows it returns. As more windows are sampled, more objects are detected, and the accuracy of the windows covering them continually increases. Sampling 1000 windows covers nearly all objects with high accuracy. This is still orders of magnitude smaller than the number of all possible windows in the image for an exhaustive search. Edge boxes are based on the observation that the number of contours wholly contained in a bounding box is a strong indication of the likelihood of that box containing an object. A contour is considered wholly contained in a box if all edge pixels belonging to the contour lie inside the box. Edges tend to correspond to object boundaries, and therefore boxes that contain a set of edges are likely to contain an object. Edge boxes use a fast structured edge detector algorithm to find an initial edge map. Neighbouring edge pixels of similar orientation are clustered together to form groups. Affinities are computed between groups based on their relative positions and orientations, so that groups forming long continuous contours have high affinity. The score for a box is computed by summing the edge strength of all edge groups within the box, minus the strength of edge groups that are part of a contour that straddles the box boundary. Candidate boxes are evaluated using a sliding window, and at every potential object position, scale and aspect ratio, a score is quickly and efficiently generated to indicate the likelihood of an object being present. Promising candidates are further refined using a coarse-to-fine search. This image shows examples in columns. At the top row are the original input images. The second row contains the output from the structured edge detector. The third row shows the grouping of edges together. Edges in green are predicted to be part of the object in the box, while edges in red are not. The fourth row shows samples of correct bounding box and edge labeling, whereas the fifth row shows samples of incorrect bounding box and edge labeling. We can see from this image that EdgeBox works pretty well. Note that these are still just object proposals. We have a set of possible locations for objects within the images, but we haven't classified these objects yet. In other words, we don't know what these potential objects are, or even if they are whole objects. Selective search starts by generating oversegments, also called superpixels, from the image. That is, it divides the image into small regions which ideally do not span multiple objects, based on the intensity of pixels using a graph-based segmentation method. Remember that superpixels are groups of pixels that perceptually belong together based on characteristics such as uniform color and brightness. It does this by computing multiple segmentations using an algorithm from Felsenschwab and Huttenlocher. It uses these oversegments as an initial seed and performs bottom-up grouping as follows. It adds bounding boxes corresponding to all the segmented parts to a list of region proposals. Then it finds similarities between neighbouring groups. The two most similar are grouped together, and new similarities are now calculated between the resulting region and its neighbours. In this way, after each iteration, smaller segments join to form larger ones. This is repeated until the whole image becomes a single region. Selective search uses 4 complementary and fast-to-compute similarity measures. Colour similarity, texture similarity, which is based on SIFT-like measurements, size, which encourages small regions to merge early, and fill, which encourages the filling of gaps. The final similarity metric is a combination of all 4 of these. As we'll see when looking at CNN object detectors, selective search was used by the RCNN family of detectors in their detection pipelines, due primarily to its fast speed and high recall. In conclusion, object proposals were tremendously useful for pruning the search space of possible positions and scales when detecting objects in images. Notice the similarity between these clever techniques and our handcrafted features from earlier in the course, in that they were the result of clever people studying the problem and trying to come up with a solution. However, in the same way that handcrafted feature extractors were subsumed into our deep convolutional networks, we'll see shortly that our deep networks can also learn many strategies to propose their own bounding boxes, for reasons of both speed and accuracy.